The next set of heat energies we're going to look at involve phase changes. I have generally classified these as enthalpies of transition, and when I talk about them in general, I might write delta H for enthalpy change, TRS for transition. So this will be my generic version of talking about phase change. But let's talk a little bit more about phase change and remember what we're talking about. So we know that our phases are going to be a solid. So my container would be full of something that might be one block, or it might be chunks of stuff. These would be very organized. Maybe they're Legos. I don't know. And then in a liquid, we have something that sloshes around. And then we have a gas. I'm going to have to put a closed container here on this gas. I guess we can make them all closed. And these gas particles, of course, we know are just moving around. So if we think about the differences between these three phases of matter, we know that our solid has a fixed size. It also has a fixed shape. And the particles are kind of stuck in one place. The bonds can vibrate, but they are in fixed positions, and that's part of why they are fixed in size and shape. So I'm going to refer to this as a condensed phase as well, which means that the matter is all stuck together. Okay? So in a liquid, we know that a liquid is a little different than a solid in that it has a fixed size, but it doesn't have a fixed shape. It can move around and flow. And that means that our particles can move. And they can move in really significant ways. You know, this particle can go over there and vice versa. They don't move as fast as our gas particles, and they are stuck together. So this is still considered a condensed phase. But it's not as condensed as the solid, so I'll put less over here. It's still condensed, but it's not in a fixed position. The gas, on the other hand, has no fixed size or shape. It can expand or it can be compressed. It does flow, and it takes on whatever the size and shape of its container. And this is not a condensed phase. It's the opposite of what a condensed phase is. It's a distributed phase. So when we look at the energy that is required for us to move between these phases, we can see that to go from a solid phase to a liquid phase, this takes energy. And so this is an endothermic process to go from a solid to a liquid. The same thing is true about going from a liquid to a gas. This is also endothermic. It takes energy. But the interesting thing about all of our gaseous or all of our energies is that each of our energies is reversible. So the amount of energy that it takes to go from a solid to a liquid is exactly the same amount that is released when our liquid turns into a solid. This gives off energy. And the same thing is true when a gas condenses into a liquid. This is also exothermic. It gives off energy. Most of the time we don't notice it, but it is actually doing that. So I'm going to say this again, that these energies are reversible. So this energy that's required to go from a solid to a liquid is the same amount in size as the energy that is given off. They just have opposite signs. So this energy that is involved with going between the solid and liquid is called the enthalpy of fusion. Okay, and we're going to use that same name whether we are melting the solid or whether we are allowing the liquid to freeze. So if we're going from a solid to a liquid, then our enthalpy of fusion is going to be endothermic, so that's positive. And if we are going from a liquid to a solid, then our enthalpy of fusion is going to be the same number. It's just going to have a negative sign in front of it. So we just change the sign. So when we go between a liquid and a gas, we have the same kind of thing. We use enthalpy of vaporization to talk about this transition. And the same thing that we just talked about is true, that when we go from a liquid to a gas, the enthalpy of vaporization is positive. And when we go from a gas to a liquid, then the sign changes and will otherwise have the same number. So these energies are totally reversible in terms of their size. The other phase transition that I've mentioned before that we aren't really talking about much here is that there are some things that can go directly from a solid to a gas or vice versa. This is called sublimation. Well, sublimation is the forward direction. Deposition is if you go from a gas down to a solid. And so we would use enthalpy of sublimation for that as well. But many materials do not go directly between a solid and a gaseous phase. The only thing that you really ever end up seeing going from a solid to a gaseous phase would be like dry ice. So if you've ever played around with dry ice, which is really solid carbon dioxide, solid carbon dioxide doesn't ever melt. It just goes directly to a gas. And so in this case, though, our values are still the same. The sublimation energy would be positive to go to the less condensed phase. And then if we went from a gas directly to a solid, then we would just swap signs. And it would be negative. So let's draw that on a diagram. Interestingly enough, it's going to turn out that our solid and our liquid transition takes less energy than our liquid to our gas transition. So I'm going to draw these. This is my energy scale. I should have left myself a little more room, so I'll put my energy scale over here. Okay, so my energy is going up in this direction. So if I want to go from a solid to a liquid, then I need to put in my enthalpy of fusion. And then if I want to go from a liquid to a gas, then I need to put in my enthalpy of vaporization. Interestingly enough, if we go directly from a solid to a gas, these are actually the same total. So the enthalpy of sublimation would be like adding up the enthalpy of vaporization and the enthalpy of fusion. So if we're coming back down the other way, this would just be our negative enthalpy of vaporization, and this would be our negative enthalpy of fusion, and of course all the way down would be our negative enthalpy of sublimation. So when we put heat into it, a system, so we talked about heating and cooling. When we heat something, we can put Q in. When we cool something, then that heat comes out again, and this is also reversible. So all of these energies are reversible. If you flow energy into a system to melt the ice, then you can get that energy back out again by letting the ice freeze again. So the other thing that we need to pay attention to, when we were talking about heating and cooling, we said that our heat flow depended on the heat capacity and the amount of stuff we had and the change in temperature. But what do we know about the temperature at which these phase changes occur? Have you ever taken the temperature of an ice cube while you're melting it? Or have you ever looked at the temperature of the water while you are boiling it, while you're actually actively boiling it? It turns out that phase transitions happen at a constant temperature. And if you've never watched this happen, it's actually fairly interesting. So you have a thermometer in your lab kit. You can boil some water and measure the temperature. And as it is boiling away, you will see that it will stay at 100 degrees Celsius. And of course, if there's something in the water, then it might be slightly different than 100 Celsius, but it should be, really close. Regardless, once it comes to a boil, you will see that temperature staying constant. All right, so that means melting is going to happen at a constant temperature and boiling is going to happen at a constant temperature. So we're going to need a slightly different equation compared to this one because we aren't going to have this temperature term in here. The other parts of it, though, are probably kind of relevant. We do need to pay attention to how much stuff we have, but this other term here, this heat capacity, is specific for heating and cooling. And we saw that that had to do with the characteristics of the material that we're dealing with. So we need a new equation, and we need new energies to pay attention to for, how much energy it takes to melt an ice cube, for example. So it turns out that we are just going to use these enthalpies. They will be values that we can find in a table. Enthalpies of fusion, enthalpies of vaporization, enthalpies of sublimation. Sometimes you will always also see them with a little bubble here. This means that this is called a standard state, which mostly means that it's at 1 bar of pressure. But anyway, if you see the bubble there, cool. If you don't see the bubble there, don't worry about it. I just wanted you to be aware. You might see it either way. Okay, so an enthalpy of fusion might look like something like this. The enthalpy of fusion for water is 6.01 kilojoules per mole. So this is for our transition between solid and liquid water. So a question that we might have might be something like this. How much energy is needed to melt a 10-gram ice cube? I didn't actually weigh any ice cubes, so they may actually have a different mass than 10 grams, but 10 seemed like a nice number. That was probably not too far off. So if water has this kind of an enthalpy of fusion, what do we need to do to figure out our total amount of heat flow? We're going to need a quantity, and we're going to need that enthalpy of fusion. Yep, you are right. We are going to have to convert this into moles. So no problem. 10 grams of frozen water has the same molecular weight as 10 grams of liquid water. And it turns out that this is 18.015 grams per mole. So that means I have a little over a half a mole, 0.555 moles of water. So my quantity then is that 0.555 moles multiplied by 6.01 kilojoules per mole. So when I multiply these together, I'll get 3.34 kilojoules. Now, a little check that is a good idea to do is to double check ourselves and say, are we melting this ice cube? Yes, we're melting this ice cube. So we did use the correct sign here, because the enthalpies of fusion and vaporization and sublimation will always be written as positive numbers. So if for some reason you are going from liquid to a solid, you're going to need to switch that sign. So you can just do this little check when you are done and make sure that you did it correctly. So just to double check, what would be the temperature of this melted ice cube? It would still be at the freezing point, right? The temperature would still be 0 degrees Celsius or 273.15 Kelvin, whatever temperature scale you're using, 32 degrees Fahrenheit, when we finish melting it. It's only if we flow more energy in after we've done that melting that this will start to increase in temperature. So as a special side check, just to review what you did in the previous video, it might be a nice idea to calculate the amount of energy needed to raise the temperature of this 10 grams of water from 0 degrees Celsius, where it is when it has melted, to its boiling point. So you can do that if you feel like it. I would recommend it, but we're going to talk instead about vaporization. So let's take a look at boiling it, right? If we are wanting to boil the water that was in this little ice cube, yes, we would absolutely need to heat this sample from 0 degrees Celsius up to 100 degrees Celsius. And then, in order to boil, we need the vaporization enthalpy. And for water, the vaporization enthalpy is 40.67 kilojoules per mole. We've already calculated the moles, so we can easily calculate what the amount of energy would be to boil this former ice cube. We're just going to take our moles again and multiply by that enthalpy. So what I got was 20.6. That looks low. Let me check it. Yeah, I think I wrote it down wrong. It's really 22.6 kilojoules. Okay, so this is the amount of energy that we would have to flow in. We'll look at them together here. So this is positive as well. This is going from a liquid to a gas. And up here, this is the amount of energy that's going from a solid to a liquid. Take a look at these two numbers here. This is very interesting to me. It takes a lot more energy to go from a liquid to a gas than it does for a solid to a liquid. I think that it's because the liquid is still a condensed phase. Those particles are still sort of stuck to each other, even though they can now move around. But with a gas, the gaseous particles have been freed from contact with each other, and so I think it takes a whole bunch more energy to do this transition. So what you should know by now is that you should take a look at when you see a problem that's involving heating and cooling or anything involving energy and classify it. So classify the steps, classify what's happening in this problem. Is it heating and cooling? If so, we're going to need this equation. So if you see a change in temperature, that's a sure sign you've got some kind of heating and cooling going on. Is there a phase change? Because you might have a problem that has multiple pieces like this. If so, then we're going to need our quantity and our enthalpy of transition. Whatever transition it is that's going on, whether it's your enthalpy of fusion, your enthalpy of vaporization, or your enthalpy of sublimation, make sure you have your correct one. So often you have more than one thing going on here, so take time to plot out a problem and identify, do I have any heating and cooling steps? Do I have any phase change steps? Because I deal with these in different ways. So in our next video, we'll look at what chemical reactions are doing, and then we'll move on from there.